This is a short video to check that you've covered all the main elements of the Calgreen analysis. First thing to check that you've done is made sure that you have a map with all the sites located on. So sites 1 to site 5 all located. Now you might want to put one of these maps on each of your site descriptions, because the analysis involves taking each site in turn, describing the geology you found using photos, locating the site using an OS map like this, and then explaining the geology of each site. So you can either have one map to show all the sites, or put a map on each of the site sections locating the sites on the map there. So looking at site 1, the sort of things you need to make sure you have in your description and your explanation are the following. Obviously it's limestone, it's micrite, which is microcrystalline calcite, and that's one of the things you need to be able to explain how it forms. So you need to be able to explain the idea of, there's a land, shallow sea, the idea that weathered material, dissolved calcite from weathering, enters a body of water. The hot environment causes the water to evaporate. That makes the concentration of the dissolved calcite, or the water, becomes supersaturated in calcite. Eventually it comes out of solution to form little crystals of calcite which sink to the bottom, fusing together as a crystalline, fine-grained crystalline limestone, which is known as micrite. So it's very fine-grained, and these crystals are probably about less than 0.5 millimeters, and that forms a micrite. Using annotated diagrams like these in your explanation of your described geology is really worthwhile doing. The other key element for this site is the fact that there are joints, tectonic joints. Now these tectonic joints, you need to be explaining these in terms of A2 geology. Now, as you know, limestone, the principle of original horizontality, the limestone is laid down in horizontal layers, bedding planes in between each beds, but they don't have any joints in when it forms. Over millions of years it compacts and forms a solid rock, and then later tectonic action, so this is a compressive force, a Pmax, from this side and from the other side. Pmax causes the rocks to, and in our case, only bend very slightly but over large areas. Now this is a compressive force, and it's a ductile deformation because there's bending, so you need to use all that terminology. However, because the outside of the fold, the bed, has to stretch further and go a further distance, there's actually tension on this part of the fold. In fact, the top part of every bed is pulled in a tensional force, and you get these cracks forming on the top surface perpendicular 90 degrees to the surface, and that's the tectonic joints. These are brittle deformations now, and they're caused by the tensional forces causing it to be lengthened on the outside of the bed. For site 1, we were looking at a bedding surface like limestone pavement, and side view you can see all the bedding planes here, almost horizontal gaps between the layers or the beds, and here are the vertical tectonic joints caused after the rock has formed due to compression and tectonic activity. Another part of the geology to explain in this site is the fossils. Now the fossils are indicative of a marine environment. These are lots of brachiopods and corals and crinoids, which if you see corals, you can use the principle of uniformitarianism, and you need to explain what that is. Corals today live in waters above 25 degrees centigrade. They live between 30 degrees north and 30 degrees south of the equator, i.e. the tropics. They like clear water. They like high energy water where there's lots of wave action to make sure there's lots of nutrients thrown up into the water. And they like saline conditions, i.e. salt water. So using all those features, we can tell from from these organisms that it was probably a warm, shallow tropical sea of the Carboniferous. Lots of these fossils are broken up, suggesting a death assemblage and the high energy wave action of a coral reef. The corals here were in life position, whereas all those other bits of fragments were in not life position, so they're a death assemblage. And here you'd show a coral with all the septa holding the corallite apart and explain the conditions of formation. Moving on to Site 1A, this was a photograph of the rock. This is the inside of the rock, which is a mafic mineral. It's probably basalt rather than dolerite. It's crystalline. It's impermeable because the stream was flowing over the top of it. What we need to also mention is that there is a slight weathered outer. You can just see it on here and more clearly on these rocks here. These rocks have been chemically weathered. Using your A2 knowledge, you should be able to explain what is in basalt, i.e. augite. 50% of it is augite, which is a ferromagnesium mineral or mafic mineral, which contains iron. And if iron reacts with oxygen in an oxidizing environment, then you get two products, as you can see on here. Ferromagnesium minerals get oxidized. This is a chemical weathering process, and the solid product is iron oxide or rust, which is this element here, and that's what you saw in that photograph. So there are soluble products which are obviously dissolved materials which are taken off by the water. So this is the sort of detail you need to put into your analysis to include A2 material. Site 2 was a mine, an adit mine, which went across the landscape unaffected by the topography, suggesting it's vertical. And these are the mounds of material that have been thrown out as they were looking for the lead. And this feature is explained by possibly a fault. So if I make this picture smaller and show you what I mean. There's the landscape. There's probably a fault, pretty vertical fault, because it just follows across the topography. It cuts across the topography, suggesting it's a vertical feature like this, some sort of fault line. And what's happened is there must have been at some point a source of magma deep down. Now, as the magma crystallizes, all the crystals form, they interlock, all the minerals are being used up. Now, there is water in a magma and lots of accessory minerals. These are minerals that are not used in not the rock forming minerals, and this hot water eventually builds up at the top of the magma chamber as all the rest of it crystallizes, and has dissolved in it lots of minerals that aren't needed in forming rocks. And eventually, if these faults are near the top of a batholith, the hot water which is known as hydrothermal hot water, hydrothermal waters with lots of dissolved minerals in them, shoot up the fault lines because there's a fracture and a weakness. And as the hot waters shoot up there, they cool, the water evaporates off, and any dissolved minerals in the so if we did a close-up of this area here, any dissolved minerals, so let's draw, there's the mineral vein would look like this now. This is the fault line down here. As the water is lost and evaporated off, minerals crystallize out in a vein, a mineral vein, or a hydrothermal mineral vein. And the first minerals form first on the outside, and other minerals form on the inside as it slowly crystallises to become completely solid. And the minerals in these veins that we saw were lead, or galena. Galena is the mineral, and barytes was the white one. So that's barytes, and these are formed by hydrothermal mineral veins due to crystallization of magma chambers. Make sure you describe fully. This is a barytes crystal. Make sure you use your green sheet to describe it fully and name it. Site 3 was the marble, the sugar marble. Now, things you need to mention here are contact metamorphism and how the heat turns the limestone into a marble. I will put all the notes up on the Geology Rocks website. On the A2 section of metamorphism, there's a little bit about how marble forms from limestone. What is hard to explain on the sugar marble is why it is sugar marble. Maybe the heat wasn't enough to crystallise it fully, because most marble is very strong. This isn't, and so this is something you could try and explain. Perhaps there was not enough heat, perhaps it's been weathered as it's been open to the elements. It's hard to explain, but you can have a go. Site 4, we can see the telltale rusting again, suggesting oxidation. You don't have to go through all the details because you've done that in Site 1A, but you need to mention it. This is basalt. We can see that it is impermeable because the water flows over the top of it. We can also see the columnar jointing, which we didn't see in Site 1A. You'd need to explain that. You'd explain that what happens is during cooling, the magma or lava would contract into a central point, causing a crack to form on the outside, and if they were doing that in an adjacent point, you would start getting these cracks, these cooling joints, and eventually they'd form a polygonal shape, and that is an indication of slow cooling magma. This is a close-up of the rock at Site 4. You can see it is crystalline, interlocking, it's fine-grained, it's a mafic rock. This is a basalt, and this is being cooled quite quickly near the surface or in contact with a cold country rock, making it cool quite rapidly. Site 4A is absolutely crucial because we have along here a contact, an actual visible contact, which we didn't have in Site 4 or Site 3. We have the light coloured marble which reacts with hydrochloric acid, and we have here the oxidised oxidised mafic igneous rock, which is the basalt, and you can see the heat from this has caused this to be baked. So we have a baked margin on this side and we have a chilled margin on this side with an actual contact, which is only likely to happen on a sill rather than on a lava flow. Finally, Site 5. The key features of Site 5 are the vertical cooling joints, 90 degrees to the cooling surface, which is down here. These are you can even see the columns, the columnar jointing, again suggesting quite slow cooling underground. When we look more closely, we can see a contact here. This is the contact. In fact, I'll show it more clearly. This is a contact line is here, and we have a little offshoot of magma here, and there's the other contact. So this is the magma. You can see this tiny little injection of magma going along. This is a bedding plane. There's another bedding plane up here. So we have one bedding plane down here, another one here. You can see the magma's followed this bedding plane and then transgressed. This is a transgressive sill which cuts across the bedding planes onto another one. So it's concordant here, discordant along here, and concordant again. Still a sill, but it has a bit of discordance at this point here. Now, some of the magma has followed along this bedding plane and it gets thinner and thinner and thinner until it eventually dies out. This lighter coloured rock is all the marble, so this is the bait margin. We'd expect a zone around here to be all basalt, here and in here, because it chilled more quickly. This is the chilled margin, this sort of zone here, and the rest further up would be dolerite because it cooled a bit more slowly. We can see the vertical joints, or the remains of the vertical joints in the marble, and lots of solution hollows where the slightly acidic rain, the carbonic acid, has chemically weathered by carbonation the marble. Close up of that can be seen here. You can see these rounded hollows are caused by the rainwater running over the surface and chemically weathering the alkaline rock. So that is the analysis. These are the 5 sites, all explained one at a time, described, explained one at a time. The next video will explain how I put this all together into a synthesis.